In mixed reality, we have access to an immersive three-dimensional space while retaining the use of physical two-dimensional displays and surfaces around us for data visualization. Instead of treating these as two separate display environments, however, we consider how data visualizations may freely flow and transition between the two. Imagine you are doing data analysis on your desktop. On a whim, you decide to reach forward and extrude a 2D bar chart out from your screen into 3D to see some additional encoded information along the new dimension, or to pull it straight out from your display and leave it suspended in the space around you. In this work, we investigate how data visualizations can be transformed between 2D and 3D. To do so, we crafted a design space of visualization transformations, which is interpreted from the perspective of a visual analytics system designer who is making these transformations available for the end users. This design space focuses on three main areas: the conditions that a visualization needs to be in for the transformation to be valid and therefore available to the user, the interactions that the user needs to perform to trigger the transformation, and how the transformation itself progresses. We now briefly demonstrate a number of example visualization transformation techniques. Many of these are controlled transformations, meaning the transformation changes depending on the manner in which the user is interacting with it. First, those that extrude a 2D visualization into 3D. Overplotting extrusion can be used to quickly identify overplotted points by simply grabbing on the visualization and pulling away from the surface, extruding the overplotted points into 3D. Shortest path extrusion uses bimanual interaction to select two nodes on a network, and pulling away encodes the shortest path distance between these two nodes along the third spatial dimension. Histogram extrusion can be used to quickly show the distribution of data points within each bar in a bar chart. Pulling further away from the surface increases the number of bins in a staged manner. Parallel coordinates plot extrusion is performed by pulling on either the x or y axis of a 2D scatterplot. The axis that was selected is now the shared dimension across all scatterplots. New scatterplots are now created at different stages depending on how far the user pulls. Next, those that flatten a 3D visualization down into 2D. The 3D scatterplot projection projects it down into 2D depending on the relative rotation of the scatterplot to the user's viewpoint. This is accomplished by simply releasing it as it collides with a surface in the environment. The 3D bar chart partitioning technique creates small multiples based on the extent to which the bar chart is intersecting with a surface. Partitions are created along either the x or z axes depending on the angle of intersection. Volumetric surface slicing is performed by pushing a volume visualization into a surface, with the slice being shown parallel to it. The remaining techniques are generic and can be applied to arbitrary types of visualizations. The matrix extrusion technique is performed by pulling diagonally from the top right corner of a visualization. The amount of elements created is dependent on the distance the user pulls. Lastly, apply linked operation performs any one of the aforementioned extrusion or flattening techniques to multiple views at the same time. We hope that this design space will help inspire a different paradigm of immersive analytics, where data visualizations can freely flow between the surfaces and the spaces in the environment.